Hi, this is Dr. Jivikas Paul. In this session, we'll discuss about columns and struts. What is a column? It is a vertical member of a structure subjected to vertical compressive load. So, vertical member of a structure is a vertical member of a structure subject to the vertical compressive load. Here it is P. This is your column. Okay. Columns are subjected to only vertical compressive loads. So, columns are subjected to only vertical compressive loads. Columns are used to support the structure. So what is the use of columns? To support the structure. Now strut, what do you mean by strut? If you see a truss, if we take example truss, so these are known as the struts. Struts, it is a comparatively shorter column and it may be vertical or inclined or horizontal. So strut may be horizontal, it may be vertical, or it may be inclined also. Struts are subjected to horizontal, vertical, or inclined loads. So, loads may be horizontal, vertical, or inclined loads. Struts are used in trusses, frames, etc. Okay, trusses, frames. Okay, in these, the struts are used. So, what is the main difference between column and struts? It is long column, it will be shorter columns, and it may be horizontal, vertical, or inclined. It is only vertical. And second difference is only vertical compressive loads will be there, and here horizontal, vertical, inclined loads may be there. Here it is used to support structure, it is used in trusses and frames, etc. Now let us say different types of columns: long column, short column. Now, what is the criteria for this? Effective length LE divided by least lateral dimension should be greater than 12 for long columns. If this ratio is less than 12, then the column is called as short column. So long column, it is a column in which the effective length to the least lateral dimension ratio is greater than 12. Short column is the ratio, if the ratio is less than 12, then it is called as short column. So what is the effective length here? Suppose if you take a column and there is a load, compressive load coming on it, so then due to this load events, there will be some buckling. This is known as buckling. So effective length of the column is the length of the column which is bending. So here in this case, effective length is same as the original length because the bending is from top to bottom here. So for different cases, let us see here next in the coming portion. Yeah. Now for circular cross section, so there is a column. If it is a circular cross section like this, then of diameter d, this is xs, this is yy. And another case, if we take the column with the rectangular cross section of width b and depth d, this is xx, this is yy. Okay. Now first for circular cross section column, if LE divided by least we have, what is this, least lateral dimension. So for circular section, what is the least lateral dimension? There is only one dimension here, that is diameter. So in xx diameter is same, yy diameter is same. So we have written LE by D. So if LE by D is greater than 12, then it is long column. If LE by D is less than 12, it is a short column. For rectangular cross sections, if LE by B is greater than 12, it is called a long column because here B is less or D is less, so it is less. B is the least lateral dimension. Okay, so therefore LE by B we have to take for this rectangular cross section. If LE by B greater than 12, then it is called as long column. If LE by B is less than 12, then it is called as short column. Now, long columns will fail only because of buckling, because of bending. Okay, long columns will fail only because of buckling, bending. So for this, Euler's theory is used to calculate the buckling load. Okay, what is the buckling load? The load at which the buckling starts, that is called as buckling load. Short columns, for short columns will fail only because of direct compression. Short columns will fail only because of direct compression. Rankine's theory is used for this case for short columns. So Euler's theory. Euler gave the formula for stability of long columns. He considered only bending of columns as direct compression was negligible compared to bending. So for long columns, direct compression is negligible. There will be only bending. So he also considered the same thing. He did not consider direct compression. He considered only bending. Okay, Euler neglected the direct compression of columns. Hence, Euler's theory is applicable only for long columns. Assumptions in the Euler's theory. The column is subjected to axial loading. This is the first assumption. Only axial loading the column is subjected to only axial loading, no eccentric loadings. Second point, material of the column is homogeneous and isotropic. What do you mean by homogeneous? Same material. If it is steel, complete steel should be there. It is concrete, complete concrete should be there. No steel plus concrete. It is not valid. Okay. Isotropic means same modulus of elasticity. Third one, the material of column is elastic and obeys Hooke's law. Okay. Hooke's law is strength is directly proportional to strain. That means if the load is removed, it will come to its original position. Okay, Hooke's law is valid. That is the other assumptions. The length of the column is very large compared to the other direction. So this B is is D. D is very greater than B. Okay, that is the meaning here. The length of the column is very large compared to the other dimension. Self weight of the column is neglected. We should neglect the self weight. He has assumed that self weight is neglected. The column is straight before the loading. Before the loading, the column is assumed to be straight. Now coming to Euler's formula for long columns. This is a column. Okay, the original length is L. Original length is L. Okay, PE is a buckling load. So due to this P buckling load, the buckling has started here. Okay, total length is L. Here effective length also LE. Okay, right. The load at which the column starts buckling is called as buckling load PE. It is also called as Euler's buckling. Okay, PE, Euler's buckling or crippling load. The formula for PE is pi square EI minimum by LE square, where E is Young's modulus in Newton per mm square, I is minimum moment of inertia in mm power 4, LE is effective length of the column in mm. Now let us see different cases. First case, both ends hinged. Both ends hinged. Okay, the load is PE, buckling load, and original length is LE. Okay, so for this case, in the formula, this is the formula, same formula. Okay, Euler's formula. Here in the place of LE, we need to substitute the L. Here LE effective length is equal to L when both ends are hinged. Next case, when one end fixed and one end free. One end fixed and one end free. Okay, this is load PE. This is original length. The beam, the column will deflect in this way. Okay, now what is LE value in this formula, Euler's formula? Let me extend this like this and let me join this. So this is your LE effective length, which is equal to 2 times L. So here, if the question is given in this way, one end fixed, one end free, you have to take in the place of LE, you have to take 2L value. Okay, when both ends fixed, like this, the buckling will be in like this. Okay, like this. So this is your effective length, bending, the portion which has bend, LE is equal to L by 2. So instead of LE, you will substitute L by 2. When one end is fixed, one end is hinged. One end fixed, one end hinged. This will be your buckling. Okay, then LE is equal to L by root 2. So instead of LE, you need to substitute L by root 2. Okay. And slenderness ratio of the column is equal to effective length divided by least radius of gyration. That means LE divided by K. Now what is K? Under root I by A. What is I? Moment of inertia. A is section area. Okay. Now let us say a problem. A hollow steel tube of 200 mm external diameter and 25 mm thick is 4 meter long. Okay, a hollow steel tube. Okay, this is a column and the section is circular, hollow steel. That means it has internal diameter and external diameter. Okay, now 200 mm external diameter, capital D is 200 mm and thickness 25 mm. You can see here, this is 200 mm and this is 25 mm. Now what will be internal diameter? D equal to capital D minus 2 times small t. Internal diameter equal to 200 minus 2 into 25, that is 150 mm. Okay, this is your internal diameter. If one end is fixed and another is hinged, see, one end is fixed and another end is hinged, that means which case? In this fourth case, that means in the place of LE we need to substitute L by root 2. Okay, Find the load the column can carry. Use Euler's formula. Factor of safety is given 2. E is given 8 minus 2 into 10 power 5 Newton per m square. So this is the Euler's formula. We know that this is the Euler's formula. So instead of E, I'll substitute rho into 10 power 5 instead of I minimum. Now if you see here, this is a circular section. For circular section, I minimum is equal to I max, which is equal to Ixx equal to Iyy. Okay, moment of inertia will be same in xx and yy. Therefore, I minimum equal to Ixx equal to Iyy. So instead of E, I have written this one. Instead of I have written the pi by 64 capital D power 4 minus small d power 4. Okay, that is the moment of inertia from I formula for circular hollow structures, divided by L by root 2. So here capital D is 200, small d is 150, L is 4000 mm. So if we substitute, we will get buckling load. This is a value. Now to calculate safe load equal to buckling load by factor of safety, which is equal to 13.25 into 10 power 6 divided by 2. This is the answer. This is a safe load. This is a safe load to avoid the buckling of column. Thank you.